All right, welcome back, everybody. Today we're going to continue on with Chapter 5. This time we're looking at 5.2, which is Quadratic Models. You're going to find your homework on page 87, and I'd like you to do question 1, 2, 4, and 5. Let's start, though, with a review of what we learned in 5.1. So here I have two situations, and I'm going to ask you to model each person's earnings with an equation. So again, feel free to pause, do the question, and then obviously press play and see how you did. All right, so the question says Joe earns $10.20 per hour. However, Adriana earns a flat pay, that should say pay, not play, a flat pay of $150 each week plus $4.65 per hour. We need to model each person's earnings with an equation where P represents their pay in dollars after each number of hours worked. So let's do Joe's first. So he gets 1020 per hour. So this backslash per means that this 1020 is the slope of the equation. So P is his pay, and that's going to equal 10.2. You can put the 0 after the 2 per hour. So the number of hours he works will get times by 1020. Now that means if he works 0 hours, he gets no pay. 1020 times 0 is 0. So he gets no flat pay. Versus Adriana, she's going to get $4.65 each hour. So 4.65, again, don't put the dollar sign, each hour she works, but just for showing up, or just for being on the payroll, she gets $150 as a flat fee. So her y-intercept, her start amount is 150, whereas Joe is 0. So Joe needs to work. Adriana can have a vacation week and she'll still make $150. Okay, so that was linear modeling. Now we're interested today, though, to tell whether data is quadratic or not. So again, I've set it up the same way as I did the last lesson. So it depends on what kind of information you're given. If you're given an equation, what you're looking for is an exponent of 2. So we say the degree is 2 in the equation. Degree, exponent. So the highest exponent you see on the x needs to be a 2. So the most common example would be y equals x squared. Now it might also be y equals 3 bracket x minus 4 all squared plus 7. So these are both quadratic. You see how the biggest exponent is a 2. Now that's not the same as, obviously, y equals 3x plus 4. That would be a line. It's not the same as x squared plus y squared equals 16. So even though the exponent is 2 here, the fact that it's also a 2 on the y, this is not a parabola or a quadratic. This would actually be a circle. So it's important that you pay attention to where the exponent of 2 is sitting. So that's how you can tell from an equation whether it's quadratic or not. Now also, we can be given a table of values. So again, if you'd like to copy these tables down, go right ahead. So if you have a table of values, you have to again make sure that your x's are in order and you're not skipping any numbers. If it wasn't going up consistently by the same amount, the table would not be useful. You would not be able to determine anything from it. And if they do go up by the same amount, so you see here 2, 4, 6, 8, 10, that's good. What we calculate are what are called the second differences. So for lines, you did first differences. Now to test whether something's quadratic, if the first differences don't match, you do an extra column, and it's called second differences. The short form is delta y, so change in y's. So these are your differences of your first differences. So you subtract your first differences from each other. So you have to do the first differences first, and then you do another column of your second differences. And if they obviously are equal to each other, the data is quadratic. So let's try these two. So like I said, the first thing you need to do is calculate your first differences, which is delta y for short. It's the y value below minus the y value above. So -4 minus -1. -5 minus -4. -4 minus -5, right? And -1 minus -4 equals, 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 equals. All right. So you can use your calculator, obviously. -4 plus 1 is -3. -5 plus 4 is -1. -4 plus 5 is 1. And -1 plus 4 is 3. Now notice these do not match, so therefore it is not a line. But we're not done yet. So now we do our next column, which is our second differences. And we're going to go -1 minus -3. 1 minus -1. And 3 minus 1. So -1 plus 3 is 2. 1 plus 1 is 2. And 3 take away 1 is 2. So the fact that they all worked out to be 2, this data is quadratic. So that's how we can determine whether a data table would be quadratic or not. All right, next data table. Let's see what we got over here. Again, we calculate our first differences. So again, if you want to get ahead of me, just pause the video here, do it, and then obviously press play, and you can see how you did. -3 minus 5, 2 minus -3, -1 minus 2, -5 minus -1. So -3 minus 5 is -8. 2 plus 3 is 5. -1 take away 2 is -3. -5 plus 1 is -4. Delta y's are next. 5 take away -8. -3 minus 5. -4 minus -3 is it. 5 plus 8 is 13. -3 take away 5 is -8. -4 plus 3 is -1. This is not linear or quadratic. So this is neither right now. This is something else. So we don't know what it is. All we know is that it is not a line because the first differences were not equal, and is not quadratic because the second differences are not equal. So it doesn't tell us what it is. It just tells us what it's not. However, if you're given a graph, what you're looking for is obviously the dots to form the shape of a parabola. So it looks like parabola, parabola. And this parabola is this U-shaped graph. And it can open up, like it does here. It can open down, like it does here. So if we were to do the curve of best fit, we again would draw a smooth curve following the trend of the dots in each case. Sometimes you only see a portion of it, like you do here. Sometimes you see a good amount of it. Notice the symmetry. So whatever height it is here, it's the same height directly across on the other side. Whatever height it is on this side would be the same height, same distance from this middle line. Now this middle line, I think that looks like the middle. This is referred to as the axis of symmetry. And it cuts the parabola in half, 2 equal halves on either side. And this is where you're at the same height on both sides, same distance away. The point at the top is where it turns around. So it was going up, it was increasing. And then here it paused, and then it started to decrease. So where it pauses and changes its mind, changes direction, that's referred to as the vertex. That's the most important point on a graph, on a parabola. And it's an x, y coordinate. So it has an x and it has a y. That would be the y value of the parabola, the vertex of this parabola. This gives us a lot of answers. So this vertex, the y value specifically, could be the maximum that the graph reaches, or it could be the lowest point, the minimum that the graph reaches. So again, in this guy, that looks like the axis of symmetry. That's where I would put him. That means the axis of symmetry passes through the vertex, which would be right there. So whatever that x value is the x value of the vertex. And whatever the height is the y value of the vertex. This y value is a maximum. This y value is considered to be a minimum. So the vertex is where you find those very important points. So it could be the maximum height a ball reaches, or it could be the minimum profit a company makes. Whatever the situation is, that's usually where we find our important answers. All right, so let's do a word problem over here where we're given quadratic data. So we're given a situation. Again, pause, copy it down, and then come right back. All right, so the situation is a ball is thrown in the air and its height in meters after t seconds has been graphed. So you see these dots? We got one here, one there, one there, one there, one there, one there, and one here. We have height, goes up by ones, and we have time, goes up by ones as well. So right now it doesn't even look like anything. So why don't we try our best to do a smooth curve through the dots, something like that, to get our parabola. So this is definitely quadratic. Describe the relationship between height and time. So as time increases up until this point, so what number is that? 6 to 6 seconds. Height also increases. After 6 seconds, so once we hit 6 seconds and we go then past it, height decreases. The ball is coming down after 6 seconds. What is the maximum height of the ball and when does it reach it? Well, the maximum height occurs right here, right at the vertex. This vertex happens to be a maximum. It happens to be at 10 meters. So the max height is 10 meters at 6 seconds. So the maximum height of the ball is 10 meters and it reaches that height at 6 seconds. When does the ball hit the ground? Well, it starts off at the ground level or thereabouts, goes up, comes down, and reaches the ground again at approximately, so I'll just say approximately, that looks like 11 seconds. So the ball is in the air for 11 seconds. Estimate. So now we're going to use our graph to estimate the height of the ball at 7 seconds. So we find, this is called interpolation if you remember. So we find 7 seconds on our x-axis. We read up. When we hit the graph, we stop and we read across. So it looks like about 9.5. So again, estimate. So it's approximately 9.5 meters at that particular point in time. So that's why we like a graph, because it allows us to answer questions for other amounts that maybe we didn't actually plot. All right, so I hope that gives you a good foundation in order to do your practice questions. Again, on page 87, do 1, 2, 4, and 5, and then check back in. All right, have a great day.